Here's a disassembled turbomolecular pump, kind of laid out in most of its pieces, the important ones at least. Here's the housing of the pump. This would go over the top. This is where you connect to your main chamber that you would be pumping. Here's the rotor, the part that spins, rotates. We have the pump base, which has the motor in it with the windings for spinning the rotor, and the pump outlet where the roughing vacuum connects. We also have the stators and the stator spacers. So the high vacuum inlet, which is right here, you can see the knife edge conflat would sit on top of this rotor assembly, and so the inlet is here. So the gas is being pumped this way down through the rotor and then out through the backing port here. Normally, you really, unless you need to do a repair, you absolutely do not want to take these things apart like this. You can mess these things up really easily by doing this. This one, I think what happened was whatever chamber it was pumping on, it must have had a viewport failure or something like that, and all the glass from the viewport got sucked into the pump. Eventually, maybe I'll make a display piece out of it. And the way that the stator is assembled around the rotor is basically one at a time, and these have a specific order that they go in. Since I don't really care about actually putting this thing back together correctly anymore, I don't need to worry about that. But you stack the spacers one at a time, followed by the stator blades, followed by another spacer, and then another stator blade, and so on and so forth until you work your way all the way to the top. Then it's assembled. And the order of these things is actually crucial for the pump operation. You can see that the angle and the spacing of the blades actually changes as you travel down the pump. And the stators kind of do the same. So you have more aggressive stator angles at the top with the more aggressive rotor angles. And then as you go down the stack, you have less aggressive stator angles matching the less aggressive angles of the rotor blades as you go down. So in operation, you know, the way that this pump actually moves molecules is through alternating stages of the rotor, which moves, and the stator, which is stationary. And basically between these rotor stages, you get stator stages that sit somewhat like this, balanced in between, and they're perfectly spaced by these stator spacers. And so up here, where you are sort of dominated by molecular flow regime, where the molecules don't really interact with each other, they have a higher probability of interacting with a chamber wall than colliding with another molecule. And so the game becomes trying to, in a statistical manner, direct their movement this way. And so as you'll have a molecule come in at some thermal velocity at a random, more or less, angle. The rotor blade is spinning this way. And so if a molecule gets hit, its velocity angle changes slightly to be favored in the downward direction. So as far as the extreme RPM, it's not so much about the RPM itself, it's more about the velocity of these blades. So the RPM requirement is to get these velocities high enough so you can transfer enough momentum when striking a molecule to get that favorable movement downwards. And you need a roughing pump here because you cannot exhaust this to atmosphere and have an effective, high vacuum up here, because basically at atmospheric pressure down here, there would be no real driving force for them to exhaust out, and so they would start building up down in these stages. And because this whole thing is operating, this big one probably wouldn't quite be 90,000 RPM. I'm guessing this one nominally is somewhere between like 40 and 60,000 RPM. All the rotor stages are spinning at the same RPM. As a consequence, the lower blades are going at that same extreme speed, and you really can't have a large load of molecules impinging on these things at those extreme speeds, because you'll load the blades, and assuming you have a motor that can keep up with the power demand, what will happen is that extreme amount of collisions with those amounts of molecules will heat up your blades enough. You'll get, thermal expansion. You might not melt the blade right away, but it will likely expand enough to seize against, the stator spacers or somewhere else, and it'll just destroy itself. And these things have such tight tolerances that enough thermal expansion, and yeah, you'll sometimes with extreme failures, you'll see blades get sort of welded to the side. So inside this pump, the rotor is transferring momentum to the molecules, getting them out the back. And this gives us sort of a direct prediction. If I introduce more gas, the turbo is, in theory, going to have to work harder to keep this spinning at the same RPM under higher load, which should require more power. And because I've just set up a nice little dashboard for controlling and tracking pressure from a vacuum gauge, as well as parameters like RPM, power, amperage, and voltage of the pump, we should be able to see some of these dynamic changes happening. This is the full system we'll be doing the turbo experiments with. Leak valve on the left. Got the Raspberry Pi up there talking to both the controller and the pump, and then we will be connecting through the online dashboard that I built for the Raspberry Pi, showing all the data. Made this control dashboard for the fuser setup, and this turns out to be really good for demonstrating turbomolecular pump action, because not only am I recording pressure here, but I have all the pump parameters. So I've got its speed being actively recorded, the amperage draw, the power, the voltage. So at the top I've got sort of an overview of system health, and below the dashboard, the first thing, this doesn't control the vacuum gauge at all, it just records the vacuum. And the turbo panel shows speed, current, power, temperature, voltage. And here at the very bottom is my favorite part of this whole thing. It's the data graphs, the active data graphs. This is the pressure graph, pretty standard, and a lot of the same functionality on these bottom graphs. We've got the motor temperature of the turbomolecular pump as well as the turbo controller temperature, and then we have the turbo RPM and the turbo power. And these make for just a great visual indicator of what's going on with the system and for these turbomolecular pump demonstrations that I'm going to do. So the importance of this is that the pressure by itself doesn't fully tell me what's going on. The turbo telemetry is really important to know how hard the pump is working while the pressure changes, or whether I've got something about to go wrong. Especially, these temperature graphs can tell you if something is seriously off. Okay, so let's watch what happens as we pump the system down. So the first thing we do is we turn on the backing pump, and that's going to, get us down that first little bit to where we can then start the turbo. And now that I have this thing properly controlled with this dashboard, I can conveniently turn the turbo on through the dashboard. So here we can see during our roughing, we started out here, and now we're kind of flattening out. This is where the roughing pump is essentially bottoming out. So now we're going to need the turbo. Now I'm going to start the turbo. Notice that we've got our voltage at 24 volts, but we're not drawing any amperage right now. So 0 amps, motor is at 25C, controller is at 28C. So let's go ahead and start it. Okay, look at that. We're already climbing speed-wise, and we're giving it now 3 amps. This is going to top out at about 80 watts of power. That's what I have it set to max out at for acceleration. All right, and there goes the vacuum, lower and lower. We're already in the -4 range, which is good. Here's our power and RPM graphs. So the RPM is steadily climbing towards that nominal 90,000. And we've got our power delivery, it's somewhere around 80 watts for the acceleration. And what we expect to see is once the pump gets up to speed and it no longer needs to be accelerating, the power requirement to keep it running should drop off because it's no longer needing to accelerate. And also our motor temperature is climbing to about 44, 45C. That's expected. We're running power through those coils, so the temperature should go up. The temperature of the controller is going up slightly, so this is all to be expected. We're at about 90% now. 80 watts still. That all looks good. And there it is. We are at the nominal 90,000 RPM, just a little under, just as we expected. As we hit the nominal RPM, our power usage dropped off. Now we're only needing about an amp to keep it driving, so we're down to 22 watts-ish, down from 80. And our temperature of the motor is now slowly decreasing as well from a peak of about 44. Now we're at 38, and that's because we're not dumping as much power through those coils, so we don't need to dissipate that away as heat. So that's an example of how the turbo behaves during a standard startup sequence. Let's now see how the turbo responds under load. So I have argon gas hooked up down here, which I'm going to feed to the leak valve, and that's how we'll provide loading gas
to the turbo. I'm going to do this very slowly with no restriction to the turbo inlet. So we're at a pretty stable spot here. It's running at full speed, no issues. It's still coming down in pressure a bit, but that's fine. Now I'm going to very slowly start letting gas into the system. And what we're looking for is a response of the gauge, because that will likely be the first thing that we see. Now we're at 1e-3, which is equivalent to 1 millitorr, and we are definitely seeing a power response trending up now. So now the turbo is having to work harder to push that gas load, and we can see that on the graph, that trend up. And so if we push this to about where the operating range for this fuser setup would normally be, which is usually in the 5 to 30 millitorr range, something like that, we should really see the turbo working a lot harder. Now we're at about the 5 millitorr range, and yeah, now the power is really spiking. Okay, there's 10 millitorr. We are going up in power even more. And look, the temperature is slowly trending up as the motor power increases. We're about 2 amps now, 49 watts. And we will just take it up a little bit more to 15 millitorr, and we'll stop there. Okay, so we're at roughly 15.8 millitorr now. We'll go ahead and let this run for a little bit to show sort of the equilibrated state at this load level, because we will do a comparison of this 16 millitorr, 15, 16 millitorr load level with a fully open restriction valve right here leading to the turbo, which is what this setup is. And then we will close this restriction valve almost fully, but not quite, and redo the same experiment and see how the power numbers compare. The idea being that with the restriction up front here, we wouldn't need the turbo to work as hard, because we wouldn't be putting as much gas through it while maintaining the same pressure level in the chamber itself. We'll go ahead and throw in a label here. 16 millitorr load, no restriction label. There we go. So now we can keep track of all these relative to the next experiment that we'll do. Okay, and now we will go ahead and close off the gas supply, and that is fully closed. We'll let this run a little bit to equilibrate it out. Now we'll go ahead and close this restriction valve to where it's just barely open to the turbo, and this should really restrict the gas path going into the turbo. And now we will go ahead and start letting gas in to try and kind of get close to that 16 millitorr previous level. We're back at about 16 millitorr. I'll add another label here. So right away, we can see that's a pretty substantial difference here. And I'm going to let this run for a bit just so we can convince ourselves that, it's not some transient behavior, but this is much, much lower power requirement. Now we're at about 38 watts, let's say, whereas before it was taking almost 60, say 59 watts to drive it at that same load. And so this is the difference of having a restriction before the pump inlet. And as an added bonus with this, you're not burning through as much gas. So if you're working with an expensive gas or something, deuterium or xenon or anything like that, you could save this is a good trick to save gas, is to restrict the pumping so that way you don't have to have as much gas flowing through to maintain whatever set pressure that you want in your chamber. As a last experiment, what we can do now is lower the speed of the pump because it has this idle mode speed setting. And we can see how doing that may affect our pressure as well as our power requirement. So right now we're starting at this baseline of 60 millitorr, and I'll go ahead and set the idle speed to 90%. So now the RPM will start dropping off, and the power as well is dropped completely. It's decelerating. It's going to go down to about 81,000 RPM. And there it is, 90%. So now it's kicking the power back on. So now it's taking a bit less power to keep it rotating at that lower speed, and our pressure is more or less maintaining. And what I want to see here is, if we go low enough on this speed setting, can we get to a point where effectively I'll have to tighten up the leak valve, because we're not going to be pumping out as much gas anymore. So here's our new baseline at 90% idle. Let's change this to 75 would be a good jump. Actually, let's do 70. Okay, and then we're decelerating again. It's going to take it a little bit of time to get down to that 70% coasting speed. Okay, and now we are at 70% coasting speed, about 63,000 RPM. It's kind of hard to see on the graph here, but we are slightly starting to go up in pressure. So we're at about 16.1 millitorr now. See, now we're using even less power, where we're down to about 22 watts from 32 at 90%, and at 100% we were at about 37 watts. And then without any restriction at 100%, we were at about 59 watts. So now we're going down to 60%. Okay, we're now at 60%. We're going up slightly, but again, it's nothing really pronounced. All right, now I'm going to put it at 55%, which is the minimum allowed idling speed for this system. It looks like we're not going to get really a pronounced pressure increase here. It's gone up slightly from 15.9 millitorr to 16.4-ish millitorr, which isn't really anything much. But what we did get with the idling is a very obvious power difference. So we stepped it down basically all the way to about 15 to 16 watts from about 35 watts at full speed. And the thing to remember here is this wattage is allowing us to maintain effectively the same pressure in the chamber as we were before. And so you can see how you can kind of play games with with the way that you drive the turbo and your restrictions to make the most of the power usage that you have available and minimize power and load while still getting the same chamber pressure performance that you would want.